Hi everyone, welcome to all of you on my YouTube channel. I'm Ankit Mishra. I am teaching for GATE Chemical Engineering since last 5 years. So I'm making this video to keep these things in motivated about GATE 2026 and embark on another examination related to chemical engineering. So also this lecture will be very much helpful for the students who is appearing for assistant engineer BPSC exam 2025. So in previous lecture, what I have started discussion about different kind of processes in process balance and control, and there I have started the transfer calculating the transfer function or deriving the transfer function for the first order process, second order process, and nth order process. So here you can see on the screen that this is the transfer function for the first order process, then there is a second order process, and after that also I have developed a mathematical formula for when we are giving a strip input in first order process having magnitude m, and what will be the output response. So here you can see after taking all of these balance and making this Laplace transform, inverse Laplace transform, we have seen that the input response, strip input having magnitude m for the first order process was found to be yt minus ys, that is equals to mkp into 1 minus it minus t by tau. So again, based on this particular formula, you can plot this, and I already have plotted these things here. You can see in the graph something like that. So but now today I'll be talking about why the transfer function of first order seems to be like that, right? So let's try to understand these things. So let's say if I'm talking about first order differential equation. If we have a first order differential equation like this way, tau dy by dt plus y, that is equals to kp into x. So obviously where y is your output and x is your input, so I can say y is your output response and x is your, right? This is how this looks like. So now if I take the Laplace, let's say this one is our equation first, taking Laplace of equation first, what will you get? Laplace of tau dy by dt plus Laplace of y, that is equals to kp into, let's say, Laplace of kp into x. So just try to understand whichever parameters are constant, that can come out of the Laplace, and after that the remaining parameters can be inside the Laplace. So let's say if I am taking a Laplace of tau is a constant, that will come outside, then Laplace of dy by dt plus obviously Laplace of y, that is equals to kp is constant, and now I can take Laplace of x. Is that clear? Laplace of x. So if I'll take these things, so I can write tau, and here if I take the Laplace of first order differential, I can write s into ys minus y0 plus ys, that is equals to kp into xs. Is that clear? So assuming initial value is 0, let's say y0 equals to 0, then what will you get from here? That tau s ys plus ys, that is equals to kp into xs. Is that clear? So from here, if I take common ys, that can be written as tau s plus 1, that is equals to kp into xs. So if I want to write in terms of ys divided by xs, that means output response by input response, that can be written as kp divided by tau s plus 1. So what you have seen, this is output by input, so that is the transfer function for the first order process, that we have got kp upon tau s plus 1. So now you would have understood that why we are getting the transfer function of first order is like kp upon tau s plus 1, where the denominator should be in first order of s. The reason is that when we solve the first order differential equation having a specific boundary condition, a specific initial condition, that y0 equals to 0, and based on this particular boundary initial condition, we are getting this value is like that. We are getting this value is like that. That is the transfer function. Okay, so I hope the motivation for this first order transfer function is clear to all of you, why we are getting this kind of transfer function. So let's try to understand for the second order transfer function. So if I am solving second order differential equation ODE, let's say for second order process, right? So let's say if I want to write second order ODE, that can be written as in terms of tau square d2y by d2 square plus 2 zeta tau dy by dt plus y, that is equals to kp into x. So again here y is the output and x is the input, right? So now let's say if this is my equation second, taking Laplace transform of equation second, we get Laplace of, I can write tau square, Laplace of tau square d2y by d2 square plus Laplace of 2 zeta tau dy by dt plus Laplace of y, that is equals to Laplace of kp into x. Is that clear? So if I take common Laplace, so tau square, and that can be written as what? S square ys minus s y dash s y dash 0 minus y 0. Is that clear? Plus 2 zeta tau is constant. Now if I want to write that s ys minus, again I can write y0. Already I have taught these things in my previous lecture. If you'll go to my first or second lecture, there you will see how to transform or how to take the Laplace of second order, first order and nth order process. And again it can be written as ys, that is equals to kp into xs. Now based on this value, if I am assuming y0 equals to y dash 0, that is equals to 0, this is the initial condition. So based on the initial condition, if it is 0, then only we are getting this kind of transform. So if I take these things, so you can write tau square s square ys plus 2 zeta tau s into ys plus ys, that can be written as kp into xs. Okay, so if I take ys common, so it can be written as tau square s square plus 2 zeta tau s plus 1, that can be written as kp into xs. So if I want to write that ys divided by xs, that is Laplace of ys domain of output divided by input, that can be written as kp divided by tau square s square plus 2 zeta tau s plus 1. So this is how the second order transfer functions look like. And why we are getting these things? Because we are solving a second order differential equation, and based on the initial condition that y dash 0 equals to y0 equals to 0, and if we are substituting this kind of initial condition for the particular second order differential equation, we are getting this kind of second order transfer function. So again for higher order also we can write this kind of equation, but in GATE syllabus or in till your BTech, I think only second order, till second order things are very important, right? I hope this is clear to all of you. Now I'll be moving towards deriving some fundamental transfer function for real process, right? So let's try to derive the transfer function of mercury thermometer. That is very important. Transfer function for mercury thermometer, right? So let's try to understand how these things look like. So let's say there is a mercury thermometer, something like that. It will look like that. Right? So if you are putting this in any liquid, something like that, so if you'll see, there will be a scale on this mercury thermometer. There are this kind of scale that shows the temperature, right? So this shows the temperature scale. Okay, now if I am putting this mercury thermometer in any liquid, something like that, I am assuming any liquid is there, and if the heat transfer coefficient of liquid is h, right, and let's say if I am assuming temperature here, that temperature of the surrounding fluid is Ts at any particular time t. So if I am writing Ts, T is the temperature of surrounding fluid at any time t, and what is Tt? That is temperature of mercury inside the thermometer, right? And this is your output that we are going to measure. Is that clear? And now if I am assuming m is the mass of mercury, and c is the specific heat of mercury, and again another parameter, that h that I'll be using is heat transfer coefficient of surrounding fluid, and A will be the heat transfer surface area, and Qt is the rate of heat transfer or heat transfer per unit time, right? Okay, great. So now if I want to derive this thing, so what you can write, rate of energy in is equals to rate of change of internal energy, right? So what will happen, let's say if a surrounding fluid is there, so if the energy which is going to enter here is Qt, so I can write rate of energy in right, that is equals to rate of change of internal energy. Rate of change of internal energy. So if I want to write rate of energy in is Qt in the form that I can write mc dt with respect to dt. So rate of change of temperature, that will get multiplied with m into c, something like that. Okay. So again Qt can be written as rate of heat transfer by convection. So I can write HA, and temperature, that is T minus, sorry, temperature of surrounding fluid Ts at T minus T at T, right? Okay, this is this can be used by in Newton's law of cooling. So let's say if I'm assuming equation first and equation second, since LHS of both the equations are same, then RHS will be same. So I can write here directly mc dT divided by dt, that can be written as HA TST minus T of T. Is that clear? And finally, if you do the integration here, so I can write d T of T divided by Ts of T minus T of T. Or if you don't want to do the integration, then just try to do this thing, because we are solving these things while using this particular formula. So Laplace, so dT by dt divided by dt, and plus h a by mc, and h a by mc, and you can write here is t, that is equals to HA divided by MC, and that can be written as TS at T, right? So here I want to define a parameter that is equals to tau. Tau I'll be defining is mc divided by ha, that is the time constant of the thermometer. Right, so now I can write tau dt by dt plus t, that is equals to ts. Is that clear? So where you can see t is the output and ts is the input. Is that clear? So now let's say if I am assuming this is equation's third and taking Laplace transform of equation third, what you will get? Tau Laplace of dt by dt plus Laplace of t, that is equals to Laplace of ts. So if I take the Laplace here, you can see tau, and what is dt by dt? S into ts minus t0 plus ts, that is equals to ts into s. This thing. Is that clear? So if it is 0, then you can write tau s ts plus ts, that is equals to ts into s, where ts is the temperature of surrounding fluid. So if I take common here ts, so you will get tau s plus 1, that is equals to ts into s. Is that clear? So finally this is output and this is input. So I want to write ts divided by ts of s, that is equals to 1 upon tau s plus 1. So that is the output and that is the input. So this is how the transfer functions look like. So sometimes the ts can be written as your ys and tss can be written as, let's say, xs. So finally I can write ys divided by xs, that is equals to 1 upon tau s plus 1. So what is ys? Ys is the temperature of thermometer, and what is xs? Temperature of surrounding fluid. Is that clear? And wait, what is tau? Tau is your mc divided by ha, that is the time constant of thermometer. And what is 1? 1 is the kp, that is the gain of the. So till now what we have seen from this particular derivation, that we are able to calculate the tau, that is the time constant, as well as the gain for the thermometer, and the gain for the thermometer is found to be 1 while using this particular formula of first order transfer function, and that already we have derived. Now if I am assuming, if I am giving a step input of magnitude of m, right, so xs will be equals to m by s. Is that clear? And now if you will derive these things, already I have done these things, so ys can be written as m by s into 1 upon tau s plus 1. And now if you take the Laplace, take Laplace inverse, Laplace transform of above equation, what will you get? Laplace inverse of ys, that is equals to Laplace inverse of m by s into 1 upon tau s plus 1. So if you see my previous lecture, there I have developed, I have derived this mathematical equation, and you can get from here yt minus ys, that is equals to m into 1 minus e to the power minus t by tau. This is the first order transfer function with m step input, right? A step input having magnitude is m, where ys is the biased value or initial steady state value. Initial steady state value of thermometer, right? So if I am assuming, let's say, initial steady state value is 0, then what is the temperature shown by thermometer? That is yt, m into 1 minus e to the power minus t by tau. Is that clear? So this will be the final formula that you will be getting. It's a very important formula. Very frequently the questions has been asked in GATE and BARC also. So let's say at t equals to 0, what will be the value? Yt will be equals to 0, right? And when t tending to infinity, what will be the value of yt? Yt will be m. Is that clear? So if I want to plot these things, if you'll go and plot these things, then what kind of curve will you get from here? So let's say this is my yt, and I am assuming ys, that is my initial steady state value, is 0, and this particular line shows the value of m. So it will go like that something, and it will reach to this particular thing, right? So at infinite time, it may be possible that the value of m, temperature, will reach to the value of m, right? Magnitude of a step input. So this is how you can derive this kind of transfer function for the first order, and the mercury thermometer follows the first order dynamics, where rate of heat transfer is equal to the rate of change of internal energy. And why this internal energy of mercury is getting changed inside the thermometer? Due to the rate of heat transfer by convection from the surrounding fluid to the thermometer, and due to this particular region, the expansion in the mercury is happening, and that's why this kind of transfer function or energy balance, once you apply these things, you will be getting first order ordinary differential equation. And once you take the initial condition, once you substitute the initial condition of ordinary differential equation after solving the Laplace transform, you will be getting the transfer function yt equals to m into 1 minus e to the power minus t by tau, where m is the step input of magnitude m, and tau is the time constant of the mercury thermometer, which is equals to mcp divided by ha. Okay, so in the next lecture I will be discussing more about what is the these things, how can you define the tau for the mercury thermometer, and after that I will be also deriving some different examples, that I will be taking the real physical example, physical models, where I will be developing a transfer function for different kind of reactor like PFR, CSTR, and tank, something like that. Okay, see you in the next lecture.